start on radio. We will start with fundamentals of electromagnetic wave. This is what is electromagnetic. How electromagnetic wave is formed. How it is traveling. That kind of idea we will discuss. And in other words, they are radio waves. We are going to discuss about the wave. You can write that as main heading, fundamentals of electromagnetic radiation. Under that, first subtopic is static electricity. Fundamentals of electromagnetic radiation. Under that, we will first look at static electricity. Static electricity. This is just an example. Rubber and wool, the creators, the wool and rubber is rubbed together. They are rubbed together. You know that there are the negative charges developed on the rubber part, the alloy part, positive charges on the wool. And similarly, this kind of experiment you would have done, right? When you rub your hair, the foam gets charged, and small particles, static particles like paper, will get attracted. You would have seen. But if it is a wet day like today, you won't see this. Normally, this kind of attraction will be there only in dry days, because the wetness in air usually short circuit this electric charge. So static electricity is normally present in dry days, in dry areas where humidity levels are low. What is humidity? Humidity is the water content in the air. When that is low, you can see this very, very often. When you get up in the morning on a dry day, you might find the hair tied up to the cotton hair, right? Because the cotton gets charged. So that is static electricity. So maybe you can throw that red balloon in the wool sweater. This one you can remember, but you don't need to go, right? Shall we draw an arrow to this and say static electric charges? Static electric charges. Why do we call them static? Because they are in a dielectric already. Insulator, it is also an insulator. So these charges can't move. They can't move because they are in insulator. Therefore, they are static charge. So shall we write that? Charges develop by rubbing. Rubbing one insulating material. By rubbing one insulating material on another. One insulating material on another, cannot move. Cannot move. Cannot move. Therefore, they cause static electricity. They cause CAUST CIUSC, they call static electricity. we find that there are two types of charges. We find that there are two types of charges. Two types of charges, in brackets positive and negative. So using static electricity, people have proved that there are two types of charges. So different materials are charged in a different way, but they identify there are only two types. And these charges are immobile because these are not conductors. If they are conductors, the charges can move and cancel with each other. But because they are insulators, once you rub it and remove, the charges will retain in each piece of insulating material. They can't move. Since the charges are not moving, we call them static. Charges are not moving, we call them static. Okay? Then what will happen? If there are positive charges on one material, negative charges on the other material, and you bring them closer, what will happen to them? Can there be a current? There can't be, because the space in the middle is also an insulator. So when you bring together, there is no current. But you still notice there is a force. So how can a force come without a current? Because of the electric field. So that's how the electric field idea is. They could not explain what is happening without identifying a field. So when the positive charges and negative charges are separated by an insulating material, there will be something flowing from positive to negative, and that is not current. That is called electric flux. Okay? Subheading you can say electric field. Electric field. We are trying to understand what are these fields. In the electric field, these are the basic ideas. But we have to remember is positive charges emit electric flux, negative charges will absorb. And so you already know this between O levels and N levels. I am just summarizing, just to remind you. Okay? Positive charges emit electric flux and negative charges absorb. Underline emit, underline absorb. One side is emitting, other side is absorbing. And we use coulombs to measure the charge. The charge also. So charge is measured in coulombs. Charge is measured in coulombs. Flux is also measured in coulombs. We should say electric flux. Electric flux is also measured. Electric flux is also measured in coulombs. Example. Suppose you take 1 coulomb of charge, how much flux will it emit? 1 coulomb of flux. Flux emitted is same as the charge contained in the material. Example, 1 coulomb of charge 1 coulomb of positive charge. Sorry. 1 coulomb of positive charge will emit 1 coulomb of electric flux. 1 coulomb of electric flux. So we observe that electric charge is measured in coulomb and also electric flux is measured in coulomb, and they are equal. But when we say electric flux, it must be something that is flowing. Flux is something that is flowing from positive charges to negative charge. But we can't see that. We can feel that. We can feel the force called electric force. When flux is flowing from one type of charge to the other type, there are certain rules they follow. What are the rules the electric flux will follow? I'm sure you studied in LS. 2 of them I already stated. One is that positive charges generation, negative charges absorption. What else?
They never cut each other.
They never cut each other. Flux line never cut each other. That is correct. Another one, they try to be away from each other as much as possible. In other words, they dislike each other. They don't want to be together. And final one is they never flow in closed loop. Electric flux never flow in closed loop. Did you remember that? Magnetic flux always flow in closed loop. Electric flux never flow in closed loop. Those are things that you should have studied in O level. We'll quickly summarize. Anyway, we don't want to go into detail. We'll summarize electric flux line. 5 points. Subheading electric flux line. This slide is subheading. So, first point is not they originate from positive charge. Other one you can mention yourself. Terminated negative charge. Third one, they keep away from each other. They don't like each other, therefore want to be away as much as possible from each other. Number 4, they never cut each other. Number 5, they never flow in closed loop. They never flow in closed loop. Never flow in closed 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 loop. That means they will originate from positive, they terminate from. If something is flowing in a loop, can they terminate? They can't terminate. There is no starting point or ending point in a loop. But these flux lines have a start, have a stop. Therefore they are never flowing in closed loop. Similarly, can you modify little exercise here now? Little exercise here. Can you take each one of them and modify to magnetic flux? Come for you. Subheading magnetic flux. Take those sentences one by one and modify. originate from what? Sorry?
North Pole.
North Pole. But wait. Do they really originate? Originate means you start there, but there is no start or no end in the magnetic flux. So they do not originate. Don't use the word originate. They are emitted from North Pole. So be careful, everything has a meaning. They are emitted from North Pole, but they are not originated from North Pole. In fact, there is no origin. No origin. No origin, we are very familiar. If I ask you, where did you originate? No one can answer. None of you might be able to answer from where did I come. If I ask you, where would you terminate? Again, nobody will know. So we are also like that. We get emitted from somewhere. But origination, we don't know. Second point, they are not terminated but absorbed. They are absorbed by South Pole, not terminated by South Pole. So see how the word should be carefully chosen. Third one, fourth one, two we need to modify. Number 3, number 4 you can spell yourself. Yeah, same. Number 3 is same, number 4 is same. So just copy them. Number 5. Different. You have to follow your notes. Look at area number 5, modify and rewrite. Those who are coming new, something I forgot to tell you is, our senior people will know. There are 2 rules we normally follow in the class. One rule is, I write the rules for you today, but you have to remember. First rule is, RWW, I don't know whether I gave it that way. That means read while writing. Read while writing. So everything you write, you must read immediately, not at home. Not at home. While writing, you have to read. If you will practice, you will be able to do it. But if you have not been doing it, that's one of the greatest mistakes you have done in your life. And now is the time to overcome. Because one of the greatest mistakes people do is they don't finish the job there and then. When you go home and have this do, you should have read your note at least once. Otherwise, when are you going to read the note? Maybe next time. Too late. So reading should occur while you are writing. That's one of the rules we follow in our class. That's why from time to time I stop the sentence halfway and ask you to complete. Why do I do it? If you have not been reading, you will know. I will not know anyway. But you can judge, okay, I have not been reading, next time I will try. So that's the guideline for you to understand you are not on line. One reason is, it saves a lot of trouble later at home, because later you have to otherwise find time to read over. If you practice this tool, which is something I have practiced throughout my life, and I don't need to read the note at home. Now, for example, this lecture I never read at home. Most of the things I do, I take only one. It is not any special cleverness. It is nothing special. Because you are doing that job right there. What happens while you write? Tell me what happens to your mind while you are writing. Now you are listening to me, true. So we are connected. The moment I ask you a pen to be put on the paper, what happens? Your mind will start wandering here and there. Home, girlfriend, somebody like that. Right? One way to stop it, best way to stop is read while what you are writing, so that you keep yourself at this moment. So the next moment I start another new explanation, you will be immediately focused onto that. Maybe if you have not been getting good results with exams, I suspect this may be the reason. So please try this. It really works, I know that. So I am a very good use of that technique. That technique anybody can master. Within about a month or two, you can master this in such a way that you don't need to read the notes at home at all. Next day you can come with the same note and immediately start from where you start. Because you are ready. Two advantages. One is that you don't need additional reading at home. Second is that in between my explanations, your mind will still be here. It will not start going everywhere. That's one rule. Second rule is this is in the class. In the class. And off the class, find information. Relevant to what we discussed in the class. That is not reading the notes only. Right? That means maybe visiting the internet or finding a textbook and reading a little bit about what is going on out there. That is to maintain our interest in the subject. Otherwise we get disinterested after some time. If you have to go anywhere in engineering, you have to keep your interest going. Keep your motivation also. Some people use the word positive thinking for it. But it is all about maintaining your interest or maintaining your motivation on engineering. Engineering is a beautiful subject area because it keeps changing. When something is changing, it's very interesting to be with it because you are not static. You can flow. You will always have a little challenge in there. However old I am still fascinated with engineering because it always keeps a challenge. But if you think positively about this, it can be the motivating factor. That itself may be demotivating to some other people. Shall I give you an example? Do you want to become a doctor or an engineer? A lot of people have asked that question. What is the difference? If you become a doctor, the system is not changing. You study this system once and it is not changing. Diseases are changing, but system is not changing. So little amount to study after. But initial studies are very hard. You have to cram everything. Very hard. And to study, you have studied. And some people lose the challenge. Of course, you might have a lot of money, but there is no intellectual happiness. Engineers are the other way around. They may not have much money. Not have much money, but they are happy with the challenge. That much I know. By talking to many engineers, they are happy about the way the systems keep changing, and they are the driving force in it. So they feel that there is always a little challenge there, and some people are really motivated by that. So if you are the type of person who likes to change and likes to keep the motivation on the change, engineering is best profession for it. It is always keeping you challenged. So think like that. Therefore, study a little bit at home to find additional information. And that information will keep your motivation right on top. Especially when you look at now. When you look at the internet, there is a lot of news about what new engineering breakthroughs have come. Last week there was an article, I was just actually doing myself. I found that there was a record number of hits when Firefox released their version 6. And that became all the servers there crashed. Because there are more than 3 million people who wanted to download this software. I just read that as a news item, but that keeps me fascinated. Because I have been teaching the load balancing units in the advanced diploma for a long time. And I thought we have really hit the top of load balancing. Any load could be handled, I thought. And suddenly there is like now we have all the servers crashed. And that means we are not perfect. And there is a challenge area. That's the challenge I mentioned. Always you are challenged. And always it keeps you fascinated about the technology. Studying is not all about cramming, isn't it? I think you have learned this hard way by now. If you have not learned the lesson, learn that now. Otherwise it will be too late. Studying is not cramming. Studying is keeping you motivated on the subject area. That is studying. And there are a lot of people who have studied the subject very well without even a degree. How? Motivation. It is how to motivate. Now these are good techniques to keep you motivated. Right? Read while writing. Please remember this. Read while writing. Find information as form. Information like products, and whenever we discuss a theory, like today we discuss structured cabling, you have a job to do. Do an internet search and find the product. Find their prices. Find where they are being used. If you don't do that, you get delayed. And it is not full learning. You lose the motivation. And sometime later you are only a City and Guilds, maybe graduate. But who cares? Who cares for City and Guilds graduate? What people care is what you know, what you can do. Isn't it? It's better to have City and Guilds qualification, but if you can't do anything, or if you don't know anything, big problem. You can't face an interview. Just the paper will not help to face an interview. So all those things. These are two techniques I have practiced. That's why I am telling you in the first day itself, for the newcomer, first day itself I am telling you this. These are very successful. Take my word. They really work. So please start doing it from today. By about month's time or 2 months' time, you should become okay. Till then it is because difficult, but keep yourself applied into that. Keep yourself motivated. Finally the result will come. When the result is there, I am sure you will come and thank me. That saves a lot of trouble for you. Studying time. And you can motivate yourself all the time. Coming back to this one. So this is why I asked you to modify the earlier sentence. I wanted you to read while write. So therefore, he wrote 5 and then you modify the 5. Number 3 is keep away from each other. Number 4, never cut each other. They are same as earlier, but number 5 is special. They always flow in close flow. Earlier it was never. Many people don't realize. You might have studied magnetism everywhere, but have you ever compared electric and magnetic? Then you know it is. Magnetic flux always flow in a loop. Electric flux never flow in the loop. So magnetic flux, when you draw, you have to draw the flux line like this. Closed loop. Only the outside we draw, inside we draw in a dotted line. All of them are loops. When the loop is very large, we don't draw it, we stop here, but it does not mean that it stops there. It is actually coming and joining. Because of that drawing, some people think it is terminating. So number 5 is a special thing to remember. Electric never cut, electric never flow in close loop, magnetic always flow in close. If you did not notice this property by today, up to today, that means you are not studying well. Time to identify. But some of you might have already noticed when you are right up there. Right? Okay. because we are studying electromagnetics, we need to study electric, magnetic, then the combination. We need to compare. Then whether it is electric or magnetic, we have a term called flux density. Shall we do that diagram, flux density? Take a cross-sectional area like this. The same cross-section area is A. Take flux line going through that, and the amount of flux we go as phi. Shall we draw that? For example, I may be taking cross-sectional area here. Cross-sectional area of A, and the flux of phi is going through. One new line dimension is A equals cross-sectional area. A equals cross-sectional area in meter square. Cross-sectional area in meter square. Phi equals flux. Phi equals flux. Under phi you can say electric flux in Coulomb. If you are talking about electric flux, it will be Coulomb. Electric flux in Coulomb. Applying magnetic flux in Weber. Magnetic flux is in Weber. Both are people. Coulomb is a person. Weber is also a person, and they have been named for the unit. On new line, if a flux of phi, flux FLUX, flux of phi is that letter. Flux of phi goes through the cross-sectional area of capital A. Flux of phi goes through a cross-sectional area of capital A. We can calculate the flux flowing through. We can calculate the flux flowing through a unit cross-sectional area. Flux flowing through a unit cross-sectional area. As shown below. As shown below. Flux divided by the cross-sectional area. When we say flux, the unit is different. Sometimes if it is magnetic, the flux is measured in Weber. Electric flux is measured in Coulomb. It may be Coulomb per meter square or Weber per meter square when you finally calculate. But the theory is common. Theory is amount of flux going through a unit cross-sectional area in space is the flux density. So if we take B, if we take magnetic flux normally denoted by phi, divide that by A, we call it B. magnetic flux density. Electric flux density, same way we but call it D, because now our flux is Q, Coulomb, divided by U. So this rule when you apply to magnetism, you get the first equation. When you apply the same rule for the electric field, you get the second one. So mention the two equations. First one is for magnetism, second one is for static electricity. The phi is measured in Weber. Right? So Weber per meter square is equal to Tesla. Weber per meter square is known as Tesla. Just mention about this is Weber, this is meter square. Weber per meter square is also called Tesla. Therefore, capital V is measured in Tesla. But here there is no special name. We use coulombs here divided by meter square. So C divided by meter square. There is no special name like Tesla for that. So it is just C over M square. That's slightly different in magnetism. One name. Electricity there is no name like coulombs per meter square. Now these values B and D, B is magnetic flux density, D is electric flux density, they become high when the field becomes intense. When the field is strong, D will be strong and D will be strong. The field strength and the magnetic flux density or electric flux density are related. Flux density becomes high, flux density becomes high when the field is strong. Flux density becomes high when the field is strong. Strong. Yeah,
Strong.
Flux density becomes high when the field is strong. Submitting motive forces. Motive forces. Motive force means what? Motive force is the force you need to keep the flux flow. Without some force, flux will not automatically flow. So some force is required for you to keep the flux flowing. That force we call motive force. If it is electric flux, we call electromotive force. If it is magnetic flux flow, we call magnetomotive force. So you can remember that. You may have studied electric and magnetic field separately. That is combined. There is one theory. In fact, we are just using different names. That's all. Theory is only one. Maybe this is the time to realize that there is only one theory for field. B is the gravitational field, or magnetic field, or electric field. There is one theory. If you master that theory, you know any field. Only names will be slightly different from each other. Theory is there. If you have realized that, studying fields is not a big job. But if you try to study each field separately, it will be a big job. Sometimes one complete book can be written on a field. But better to compare and learn, then it is easy. But what we are doing is we are comparing. We are first defining what is the motive force. How do you define? Motive force is force required to keep the flux flowing. We don't specify electric or magnetic. Keep the flux flowing. It could be gravitation flux. Keep the flux flowing. Come in and now for the fan to continue, we need some energy. Somebody must flow energy into this. For the light to continue to flow, some energy must flow in continuously. That is the rule of energy in the world. Neither created nor destroyed. It is just exchange. Similarly, the motive force is like this. You need the electromotive force to keep the electric flux flowing. You need the magnetomotive force to keep the magnetic flux flowing in a circuit. Right? The motive force is the force needed. It's the force needed to make the flux to flow. Force needed to make the flux to flow. Force needed to make the flux to flow in a circuit. Then you can define very well known EMF, electromotive force. Force needed to get the electron going in a closed loop. This EMF, I think you have studied that is called voltage. Force needed to move electrons in a closed electric loop. Can you define magnetomotive force yourself now? Again, this is reading while writing. So concentrate now. Look at the radio note and write invention. Magnetomotive force. Will there be magnetic flux in a closed electrical circuit? No, isn't it? In a closed electrical circuit, you don't get magnetic flux. You need a closed magnetic circuit in order to get magnetic. So you have to change this word. Closed electric circuit should become closed magnetic circuit. Because electric circuits can't carry magnetic flux. So this must be changed to magnetic. Closed is correct because magnetic flux flow in closed loop. So magnetic force, magnetomotive force, MMF, the force needed to drive magnetic flux through the closed magnetic circuit. Before coming to field intensity, let me explain what is the electric circuit, what is the magnetic circuit. So think of electric circuit, what are the resistors there? There are battery, wire and resistor. There are electromotive force, E volt, current is carried, resistance is this is an electric. There will be electric current in a loop. Can you draw a magnetic circuit similarly? Let you tell him. Take the page into two columns. First column you can draw this. Right side you can draw You can think of how can I drive magnetic flux like the car? What do I need? Ask yourself someday. I'm taking another year, study the magnetic and come now. Electric magnetic fields are very fascinating. For the reason that you can't see them, they are invisible forces. Some people, just because of the same reason, they dislike. Very unfortunate. But I like these fields because I can't see them. It gives me invisible force, which other people can't find. But telecom engineers can communicate over long distances now. Only yesterday we got the message from Mars. What was the message? If you have been reading additional information and text. What is the message from Mars? USA has sent this Mars Explorer and it landed about 2 weeks ago, right? And then it has been taking the soil from the map. And what was the message yesterday? They found water. This was the message. And earlier it was thought that on that soil there is no water. So yesterday news, if you look at the internet, you will find they have found water on Mars soil. News. Some additional news now. Invisible forces communicate. Otherwise, how can we know that something has happened in Mars yesterday? They have decreased and tested. By today, I know. There was what? Invisible way to communicate. It gives you a lot of invisible force. So if you are the type of person who likes to handle the force like that, a force which cannot be seen by other people, you don't need to do this. But some people like to see the force. So they choose mechanical engineering. They can see a piston firing. Right? They can see the wheel turning. Easy to understand, so you become some basket manager and start repairing the vehicle. You are working with the field forces that anybody could do. The telecom is not built like that. And that itself is why it is research. It has lots of invisible forces, long distance communication, various electric forces, magnetic forces, etc. You can generate. For example, your brain right now produces the various waves, alpha, beta, theta, and people are still not sure how they come. Lot of invisible things that we still have to uncover. Only a person who has studied these kinds of fields will be able to take that kind of a challenge. So, about a month ago, I got two visitors from UBC, University of Berkeley, California. And UBC has joined with University of Atlanta in UK. And we have a research team working there. And they wanted to send $3,000 gadget to me. Okay? And I just checked what they want me to do. Okay? And their idea is to develop something like calmness index for people, because this gadget has become very popular in UK. The gadget is some belt here which you wear, and then it is transmitting wirelessly to this. So I don't need to wear any wire, I just wear the belt and I can do my work. And this gadget will keep monitoring what I am doing. What I am doing in the sense, what kind of waves I am emitting. And there is a lot of research to be done in that. But that is not research they wanted me to do. They wanted me to develop a local team here who would develop a calmness index to the person. That means how calm you are at this moment, how calm you are. If you can give it like an index like 0 to 100, they are very happy, which they can't do. Because why they can't do it? Because they don't have calmness. Calmness is something we have. Right? They are always very busy, they are not calm. That kind of people, they don't understand that. But in US market, this gadget is selling like ice cream. $3,000, and they have made millions of within few months. Because everybody is interested in calm. So you can see how difficult lifestyle is. If that many equipment sold. So People are searching for calmness, and now they turn to atheists. People like us, who look like more calm than they, who do less work sometimes, and maybe we enjoy life more than them, I don't know. And they want us to develop a calmness in us. So I'm waiting for their budget to come. It will arrive in 1-2 weeks' time. And then we have to, already we have a meditation design team, which we are trying to put this into an index. But it is not for meditation. It is to measure the calmness in a professional way. Because calmness is something you can sell. Something you can sell to many people. Calmness is a luxury. And you can, if you are smart enough, you can sell it. That's what that company is doing. And their local branch is also working on that. At Rajagiri they have a local design team. They are also working. So, basically the message is, there are a lot of invisible things in the scientific world there. They don't see these waves, brain waves, and therefore they can't really design a calmness in. Of course the gadget is there. They don't know what to do with it. Problem is that in order to measure, you have to get hold of a research team who can do meditation. So therefore the demand is on 8th area. Another area where invisible forces are being explored even by the developed field. I am not saying that we have invisible forces, but there is a lot of interest there. There is a lot of interest there because they have realized that business is not the solution. It can give you a lot of money, but can't give you pleasure or calmness. So we are now thinking in a reverse direction. There is heavy demand there, according to that company. If we can make a breakthrough, there is a big demand. So, if you are fascinated with invisible things, try this. Try electric field, try magnetic field, how they work. Try alpha wave, beta wave, theta wave, which is coming from the mind. There are a lot of messages there which we don't have knowledge to understand. That's very interesting area. So, let us start with the basics. Can you do the basic magnetic field? Without that basic we can't go anywhere. We have gone very high level like calmness in it, but right now we have a challenge of drawing a simple magnetic field. Simple magnetic field. Unfair, no? I told the electric circuit, it seems to be easy for you, but that's a difficult one to use. Which is not the correct one. Magnetic one is easy. Magnetic circuit is easy. Magnetic flux flowing through a material, and a magnetic force driving the magnetic flux. I'm sure you have learned this somewhere. Just compare with this diagram and this. If you want to draw that same as this one, then draw it as a loop. You can take a magnetic pole like this. You would have seen some transformers. Even if you have opened your booster there in the antenna, you would have seen this transformer pole. Then you need the flux to go through this. But who is driving? You need a battery, and you need a magnetic battery. A magnetic battery is something like this. This is a magnetic battery which in turn high current sent to that. You will get the magnetic force driving. If you could not do it, maybe you have studied magnetism, but in isolation, without comparing with electricity. The electric circuit, magnetic circuit. Look at how similar. You have electromotive force, you should have magnetomotive force here. Magnetomotive force is measured by number of turns multiplied by the current here. And then you have current here, corresponding to that you have flux there. Electromotive force, magnetomotive. And you have resistance there, corresponding with that. In this material, you have what is called reluctance. Yes. This is reluctance. Magnetic materials all have reluctance, whereas electric materials have resistance. So you can see how similar the electric circuits and magnetic circuits are. These are the things to notice. These things are not as difficult as you think. Your ability to simplify is what is required. People have complicated it enough for you in the textbook. But we have to develop ability to simplify. I noticed that not many people could draw the magnetic circuit. That is a big problem. Why? Because our mind is too complex. You have raised your mind and you have complicated your life. Simplify your life. Then it will be easier to understand. Electromotive force is electric current driving through a loop. Magnetomotive force is magnetic flux driving through a loop. And there is opposition for the electric current for resistance. There is opposition for the magnetic flux for reluctance. So that's all. That's all. It's not a big deal. So why don't you write those under each one? In your own words. One thing is opposition to electric current is resistance. Opposition to magnetic flux is reluctance. Opposition to electric current is resistance. Opposition to magnetic flux is reluctance. This is the electric current battery. This is the magnetic battery. Magnetic flux battery. Electric current battery, magnetic flux. You can generate magnetic flux using a coil. So there are electric batteries, there are magnetic batteries. Unfortunately, magnetic batteries, they don't sell. You have to make it. You can make it to any level you want by increasing the number of turns. So we have the simple rule here. Simple rule is that EMF is equal to R times I. It's equal to Ohm's law. Similar to Ohm's law, here we have MMF equals S into phi. See how similar the equation? Electromotive force is opposition multiplied by the current. Magnetomotive force is opposition multiplied by the current. Similar to the Ohm's law. Similar to Ohm's law. If you like, you can think of it as magnetic Ohm's law. Remember, there is no like just right. Way to think magnetic Ohm's law. motive force is equal to the opposition to the flow multiplied by the flux. Here flux is the current, here flux is the magnetic. This is the part which is flowing, this is the opposite. This is the part which is flowing, this is the opposite. See how similar? So if you just remember the Ohm's law, that will be enough. You don't need to remember the other one. But some people can both. Very unfortunate, isn't it? 60% of your memory is wasted. When you could cram only one equation, why should we cram two? So that is smart way of study. Minimizing the amount of work for the brain, and that means to simplify, not complicating. Now in engineering also some people think if you are to study engineering you have to understand very complicated things. Again wrong. Best engineers are the people who have simplified the big things into something very useful or very simple. Finally it becomes a hand carry tool. Look at the telephone, for example. Even the telephone they have simplified, not complicated. How much they have simplified is that you can carry it. Finally the application should be simple. That means our thinking also should be simple. I mean, like say things which you disagree, but this is the way we have to train ourselves in order to go forward. Otherwise we are unnecessarily complicating our life. We are making it more complicated than it is. Okay, so on a new line you can write. So the science understand the similarity between an electric circuit loop and the magnetic field loop, magnetic circuit loop. If you want to write one more point here, resistance in your certificate level, what is the equation for resistance? Resistance is equal to L divided by rho times divided by A. We use that. So this same thing can be written as rho is 1 over sigma. Rho is the resistivity, sigma is the conductivity. L divided by A. Similarly, if you have studied the magnetism, you would already know from your A level, reluctance is given by this length L divided by what? Mu times look at this. L over sigma A, L over mu A. L and A are the same, isn't it? Sigma is the ability to conduct electrons. Mu is the ability to conduct magnetic fluxes. Again you can see similarity. You don't need to cram that. If you remember that, that is enough. So likewise I can show you lots of similarities of how to compare magnetic and electric, but that is not our objective. So I am deviating a little bit from there. We will define one more term now, which is called field intensity. So write a new heading called field intensity. Field intensity. Field intensity means motive force per unit length. Motive force per unit length. is to move flux over a length L. But if you divide the motive force by the length, you will get motive force available per unit. That is called field intensity. So you can we apply a motive force. We apply a motive force to move. That's why the name motive. Move flux through a circuit of length L. Move flux through a circuit of length infrared. Therefore, if we divide the motive force by the length of the circuit, we divide the motive force by the length of the circuit, we get the field intensity. Earlier we noted, when we increase the motive force, field will become strong. But now we want to measure the field, because anybody can feel the field, but engineers should be able to measure them and work with those fields. And in order to define how strong a field is, we have come up with this notation, field intensity. So if it is electric field intensity, this is how we define. Electric field intensity category is electromotive force per unit. Look at this, motive force per unit. If you substitute electric there, electric field intensity is electromotive force per unit. If you substitute magnetic there, magnetic field intensity is magnetomotive force per unit. So just modify the theory as you like for the different fields. But it is one theory. One theory, field intensity means motive force per unit length. That you have to remember. If it is magnetic, we call it H. Magnetomotive force per unit length, magnetic field intensity. Normally given by letter S. Electromotive force per unit length, electric field intensity, normally given by letter E. And this is measured in volts per meter. This is measured in amperes per meter. Volts per meter or amperes per meter. Since most of you have done A-levels, I am not introducing anything new here. But I am just introducing a new way of thinking, which you might have totally missed. So it shows how easy we can miss simple things, isn't it? Okay, so EMF per unit length is electric field strength. Something I forgot here. That the word field intensity is sometimes called field strength. Field strength and field intensity means the same thing. Have we read? Field intensity is also known as the field strength. strength. Therefore, capital E can be called electric field strength. Capital E can be called electric field strength. Capital H is called magnetic field strength. When you measure a signal, it is now easy to measure EM. Sorry, it is now easy to measure capital V. In the market, you have a gadget called field strength meter. Field strength meter has a little antenna. You have to tune that antenna to the signal, then it will indicate how many volts per meter strength you are receiving. So that is the real practice. Now this is the theory. In practice, there is a gadget in the market called field strength meter, and you should be able to work with that if you are a telecom engineer. If I want to measure the field strength of, say, Rupavahini signal here, I get hold of the field strength meter, erect the antenna, typically 3 meter high, then adjust the dipole length to Rupavahini antenna size, and then we will get the reading called capital E. And what is the capital E normally here? What is your idea? And standard says it should be a little bit higher than 55 dB microvolt per minute. So that is the professional way of measuring. Then you know the signal strength level. You have now measured, you can compare with the others. It was invisible earlier, but now it is visible. Using meters you can always identify. That's the practical side of it. And you know, electric fields are there not only due to telecom waves, due to natural things also, isn't it? Right now in this room there are lots of electric fields, and you are right buried into them. It's right going through your body. Did you know? It is not a surprise because we normally forget this thing. It's right now penetrating your body. Many things. Just even a radio or a TV here, it works. So the thing is here. Thing is right here. And sometimes there are natural causes. Now lightning, we know, is due to the electric field activity between clouds or within a cloud. And the electric field strength in the lightning is important to know. Then we can measure how much of induced EMF will come down. Whether it will be damaging, we can measure. There are people who have risked their lives to do that. I am talking about electric field strength meter. And these are the early people who did that. You know the well-known kite experiment by Franklin, right? He tried to send a kite into a cloud and measure the electric field intensity inside there. And luckily survived, right? Because now when you send a kite into a cloud, it can arc into the kite. And then right into the earth, there will be a lot of current. And there are a lot of people who died due to this kind of experiment also. But he invented what? He invented what you use right now at the top of the building, known as Franklin rod. Have you seen this? This kind of a rod on top of towers and buildings, which is his invention, Franklin rod. Because he was trying to measure the electric field intensity in the cloud. Who would think like that? Do we get that idea? I should fly a kite and try to get into a cloud and try to measure. Everybody will say, don't do that. But there are people who have gone up to this extreme in order to measure. In order to measure and understand. Real engineer. Of course, one may think it's very foolish to do that. But on the other side, it tells us how important the measurements are. Without measurements, we are not engineers. To be professional, we should measure things. And we should be very accurate in the measurement. So people have tried this kind of experiments just to measure electric field intensity inside the cloud. Just to show you one extreme set of people were there, and because of that Many people's lives today are protected because of Franklin, just because he risked his life. Let us compare these two. On one side, divide the page into two. So we write that heading, flux density and field density. I've got a little bit of static electricity problem in the projection. Did you know? You can read the previous slide. The previous slide is gone from the computer. Where is it? How did that come to? In the computer it is gone. Coming inside this. Having static electricity in the plane to which the light is getting projected. So it might be a developing problem. I will have to worry a little bit. Let us see. In a dry day it might not appear. We don't know. But you can see the problem. Now this part is definitely due to static electricity. And this is the bad side of it. It might leave some image of the earlier thing on the plane which is mixed with the new one. Good side of static electricity is photocopying, isn't it? Photocopy works completely on the static electricity. So these are science principles that you can adapt to various engineering gadgets. And some are worried about what is the relationship between science and engineering. Now this kind of thing is not engineering. Studying electric field is a science, it's physics. It is physics. But it's very closely related with engineering. So what is the difference? Now studying a transistor is physics. Transistors are invented by people who study physics, not by engineering. Then what do they do, engineering? They are studying. Remember, you want to become engineer, isn't it? You know what they are supposed to do. They are supposed to borrow these ideas from theoretical people and make it a practical device that can be used by men. So the best use is what the engineer is worried about. What is the best way to use it? So we borrow the principles from electric fields, magnetic fields here and there, and we generate electromagnetic waves using antennas. So gadgets which are applicable to day-to-day life is normally designed by engineers. But the real brain work may not be from the engineers. Brain work may be coming from people who have studied fundamental science, chemistry, physics, that kind of thing. So that is why the government also wants you to study physics and chemistry before engineering. In the syllabus now we have gone through that. So some governments want you to study it like that. I don't know whether it is the correct way to study, but real brain work is coming from there. Engineers really convert the idea to a device that people can use. And therefore anybody can become engineer. If you want to do real brain work, you can study physics, chemistry. But if you want to make gadgets for people, you can become an engineer. You don't need qualifications for that. Some people think engineer means somebody who has a degree, engineering degree. Completely wrong. Because if you have to look at the role he plays. The role he plays is he borrows ideas from these great thinkers and then converts it to very simple devices that people can keep using. That's the role of engineer. If we compare these two, this is the relationship between electric field and electric field intensity. Now earlier I gave you this, later I gave you this, and I am going to relate the two by this way. There is an equation called D equals epsilon times P. D equals epsilon times E. This is now pronounced as epsilon. Epsilon. Like you can mention EP, SILON is the way to pronounce epsilon. It's a Greek letter. It is called absolute permittivity. Name is absolute permittivity. Absolute permittivity. I define permittivity later. And then absolute permittivity is sometimes written as epsilon R into epsilon naught. Absolute relative free space. You can remember this as R for relative. This is for absolute. So some people might give it as a relative value to permittivity of free space. And many people don't understand what is permittivity. What is the meaning? Permittivity. Permittivity is ability to permit. Ability to permit. What do you permit? The flux, electric flux. Ability to permit electric flux is called permittivity. So if there is a material which has no ability to send electric flux through it, it has higher permittivity. Simple as that. You know, it's unnecessarily complicated. So similar equation on the other side is, sorry, please write this button. Absolute permittivity is the ability of the medium to conduct electric flux. Ability of the medium to conduct electric flux. Now, your body, for example, has a certain permittivity value because your body conducts electric flux. Okay, let us see how similar it is on the other side. Now, what is this? This is electric. No, we studied it. You should be reading while writing. This one is electric flux density. This one is electric field intensity. Look at the similarity on the other side. Magnetic field, magnetic flux density, magnetic field intensity. Ability to conduct magnetic flux. Here, ability to conduct electric flux. See how similar the two sides are? Then we call this absolute permeability. In English, what is the word permeate? Permeate means go through. Permeability means ability to go through. Better to compare these two, then you can see how similar the two sides are. something on your own, try to combine these two equations into a single equation in words, not in these, is, etc. Don't use any letter like that, but just convert it to words. Combine the two equations into single. Right? I will give you 5 minutes. Try to combine these two into a single. Remember, learning means trying yourself. Right? I'm only the helper. So if you can get it right, you have the ability to simplify. I'm just checking your mind's ability to simplify an idea. I have given 2 ideas. I want you to simplify them into a single idea. Single equation. Take time because now you may have, I don't know, maybe 50 people here, but out of this about 10, 15 go to the advanced system. Others drop out. Because others don't try. People who try go. So simple like that. So there is an opportunity to try. Please try. Earlier we said is intensity equals motive force over length or something. So I want you to write it like that. Not like English letters. Not using English letters. But by sentence. First of all you have to see the similarity, then convert that into an idea. Single equation. On the left, what do you get in both equations on the left?
Flux density.
Flux density. So if you have thought like that, flux density on the left side equals, second letter is ability to conduct. Ability to conduct multiplied by
Field intensity.
So if you wrote like that, you are great. You can think of two things as one. And you can simplify your amount of cramming at home. You are a person who could go through an exam by studying minimum. But if you are unable to do that, you have homework. Sometimes we may not be able to do it immediately. You have to work on that, work on the weak area for a few months. Because there are things which will not immediately improve. Like read while writing is a technique which needs a lot of time. And this is another technique. In order to simplify things, we are not normally used to. Many people are used to complicate the things, get things complicated and get entangled into problems and keep thinking about the problem, entangling yourself more and more into that. You never find a solution there. The person who finds the solution is the person who can simplify. Try to define the problem and try to see, can I solve it this way? Like simple ways of thinking can solve it. Right? We have to understand that. Ability to simplify is a very great strength, key strength. So if you could simplify this into a single level like field intensity is equal to ability to conduct multiplied by field flux density is equal to ability to conduct into field intensity, it's there, because then you can forget about magnetism, forget about electricity. General rule is flux density equals ability to conduct multiplied by field intensity. You can apply it to gravitational field, you can apply it to electric field, you can apply it to magnetic field. See how simple the thing is? And I would go one step further. I would like to think like that. I would think like flux density is proportional to the field intensity. And the proportionality constant is the ability to conduct. I prefer that. Whatever the field, flux density is proportional to the field intensity. That means higher the field intensity, there will be more flux density. Proportionality constant is the ability to conduct flux in that material. It is another easy way to say. In fact, that is how I learned. I don't remember this formula, but anyone, if they ask me the formula, I can immediately write. 6 second thinking is required, that's all. But I don't remember anyone. So you have to be smart, right? Get the ideas from here, and by applying them day by day, it will take months, definitely, 2 months, 3 months, that you can do. Consistency is very simple. Right? This could be further simplified. By stating flux density is proportional to we write like that. This is the symbol we use and we pronounce it as proportional to. Proportionality constant. Simplified way of thinking, and you can apply it to any field you like, any field. And there are new fields which are coming now. Some people have invented plasma field recently. So they have found that this tool can be still applicable to plasma. Likewise, learning something general is very powerful. You learn only once, but apply many times. Then another similarity between the two is now electric field we may say epsilon T is epsilon R into epsilon naught. Similarly, magnetic field mu is mu R into mu naught. Just write the two as comparison. You can see again how similar the effect is. relative ability to conduct electric flux. With respect to, when you say relative, it must be with respect to something. And free space is our reference. So you can copy that. Relative permittivity and relative permeability here. Relative permittivity is relative ability of the medium to conduct electric flux with respect to phase space. Relative permeability is the relative ability of the medium to conduct magnetic flux with respect to phase space. And these values are available in engineer's handbook for various materials, for wood, for metal, for water, air, for different materials. You can read these values from the table, and the tables are available in the internet, and also they are available in the engineer's handbook. In any library you will find engineer's handbook, and they have these tables. If you work with the material, you can find what is the relative permittivity, what is the relative permeability. Like calmness index I mentioned. For example, now you can run, you can run. What is the ability to run? It varies from person to person. So if I ask you to run, I will be the last person. Because my ability to run is not very good, but yours is definitely high. So, as a human, I have many abilities. You have many abilities. You have ability to run, ability to see, ability to present, ability to so many abilities. Likewise, if you take a material like water, it has many abilities. Ability to permeate is permeability. Ability to permeate is permeability. Then the water has other abilities as well, mechanical, electrical properties. But likewise, if you take any material, these are those abilities, just like you. We give different words to define that ability. So we are looking for that ability to create an antenna. We want a material, we want copper, we want aluminium. Then I should know what is the ability of aluminium to conduct electric flux. Otherwise I can't make an antenna. I should know what is the ability of aluminium to conduct magnetic flux. That's why these things become important later with practical work. Okay? These abilities are abilities of a material. Sigma is the ability to conduct electrons. Epsilon R is the ability to conduct electric flux. Epsilon mu R is the ability to conduct magnetic flux. Suppose you take copper. Just take a piece of copper. Which ability is the highest? Which ability is the highest? Is it sigma high? Or is it mu R? Is it epsilon? Now you know copper very much. Oh, you know aluminium. I think you are using it at home. Right? So tell me which one is the strongest out of these three? These are different abilities of that material. So if you have realized, recognized that ability, you will be able to tell me. which is the highest one? Sigma. Sigma is the conductivity. Conductivity is 1 over resistivity. So is it mu r or is it epsilon? Epsilon dash sigma. Sigma is the correct answer. Sigma is the correct answer. Good. Because in copper, mu r is 0. Epsilon r is 0. Did you know that? Copper cannot conduct electric flux at all. Copper cannot conduct magnetic flux at all. Copper is a metal. Metal has the ability to conduct electrons. If you take any metal which is a perfect conductor, relative ability to conduct electric flux will be 0. Relative ability to conduct magnetic flux will be 0. The conductors don't conduct magnetic flux. Conductors don't conduct electric flux. What about the air between you and me? Can it conduct electric flux? It can. It is one of the good conductors. But it can't conduct electrons. The air between us has no ability to conduct electrons. Therefore, sigma is 0. But mu r, epsilon r are good. They are good because electric flux can conduct, magnetic flux can conduct. So that's why I said different materials have different abilities to different levels. That's why you should measure the ability to run, ability to walk, ability to present the person. Then only we will know the person well. Same way, for you to know a material well, you should be able to look at epsilon, sigma, mu, and then tell what it is good at. So that's the way to think as an engineer. These are different abilities. But remember this rule, if it is a metal, perfect conductor, then mu r and sigma are 0. They can't conduct electric flux. They can't conduct magnetic. Many people think a good metal can conduct electric flux. Completely wrong. It is the other way around. Best metals do not have any ability to conduct flux. They have the ability to conduct electrons. Yes. Perfect conductor. Right. Copper, aluminium, have high sigma, which is like a conductivity. The ability to conduct electrons. But they have nearly zero mu r and epsilon r values. They have nearly 0 mu r and epsilon r values. They cannot conduct electric flux. Or magnetic flux. They cannot conduct electric flux or magnetic flux. However, good insulator such as air, wood, plastic, etc. have high epsilon r and mu r. But nearly 0 sigma value. sigma. Therefore, a good TEM wave, a TEM wave which we are going to discuss here. TEM wave is the electromagnetic wave. E and M means electromagnetic, T means transverse. I will explain later. But think of electromagnetic wave, therefore a TEM wave, we find it easy to go through what kind of material? Can you complete the sentence? If you have been reading. You will go through what?
Insulator.
Insulator, correct. Go to insulators then conduct. Now that's something invisible, isn't it? Conductors, many people have studied electricity. But just going through insulating material is special thing about electromagnetic waves. And that's why I said right at the moment there are a lot of waves going through your body and your body is insulated, isn't it? If it is not an insulator, it won't conduct. Suppose you are made of copper, you will be very safe from electromagnetic. You can't go through it. If you are made of copper. Right? There will be many people who will take you because copper is very expensive. And you know, even the telephone wires they cut and take to less. So better you are not made of copper. But if you are made of copper, you will be safe from electromagnetic waves. They can't go through you. They can't penetrate. But now that you are insulated, you have good mu r, you have good epsilon r value. So these waves will easily penetrate your body. And you happily allow also, you don't oppose. And because it's invisible, many people don't know. So some waves, could be damaging also. Especially like microwave, high power, is sometimes damaging. But since we can't see and we didn't know about it, we are not worried. That's how bright people exploit other people. They don't tell you what it is exactly, but you will know later. Okay. Now we come to the radio wave. We have finished the basic theoretical ideas needed to study electromagnetic waves. In other words, we have finished summarizing what we have learned in error. Let me go back. Where did we start? We started saying there are two kinds of electricity. That in static electricity there are charges, positive and negative, and they are immobile. Because of that, there will be flux flow. We found 5 characteristics of flux, electric, 5 characteristics of magnetic flux. Then we define magnetic flux density, electric flux density. Then we define magnetic field intensity, electric field intensity. And we said electric field intensity is the most common measurement in practice. Without that, you can't survive in the telecom field. Everybody should know how to measure EMF measurement. Later on we are coming into that. And then we learned that ability to conduct, ability to pass electric field, ability to pass magnetic flux are separately measured by parameters like sigma, mu r, epsilon. And they give a good idea of what kind of materials are good for waves, what kind of materials are bad for the waves. So this is the subject we will be studying so far. I would like to leave radio waves for next time. So today I will stop in early. Next time we will completely start on radio waves. In the meantime, if you have A-level notes with you, now is a good time to go through it. Now is a good time to go through the electric magnetic types and quickly grasp this idea. and be ready. Thank you very much.
Idea. Can't idea.